Let's just go ahead and start and read the chapter 3 or the slides, I guess, and we'll meet back here at 11.
Cool.
Okay.
Joseph.
Okay, we've reached 11 o'clock. So the reading period's over. I wasn't able to finish, but I wonder if, let's see, our leads are here. Let's see, we had 2 people who were going to lead one. Let's see. Sorry, I'm going to find. Yeah, let's see. We had Anirudh was one, and Steve Roberts was the backup. So are either of those here? No. Okay. Well, then I guess anyone that wants to can start the discussion.
Should we maybe go over the exercises? There are mostly questions, like theoretical, and that would drive our discussion probably.
Sure. I didn't get to the exercises for sure. I mean, but if you wanted to start that discussion, you're welcome to.
Yeah, I think so. That will be the great place to start, and then we can refer back to the text too to take or understand concepts that we do not.
So,
Well, I was looking through. Yeah, go ahead. Sorry.
I'm just saying that someone should share a screen with a book probably, right?
I can do that unless you have it open. You can share it if you want. I'll do it then. Let's see. I have to find the controls on Zoom. There it is. Share screen. Screen to share. Okay. Can everybody see? I'm sharing the book. It's coming into focus there.
Yeah, I can see.
Yeah. Okay. So we can start at the beginning. I actually switched from the book to the slides, but the slides are a little bit heavy going too. Arto, did you want to begin talking about one of the problems, or?
Yeah, I could start. Actually, it's not like I'm saying that I have all the answers. I just was suggesting a course to drive the discussion, but yeah, let's find the first exercise and we
example 1.
Yeah.
Let's see. So this is just an example though, but the bioreactor.
Yep. So yeah, so the exercise 1, devise 3 examples, example tasks of your own. And yeah, here, this is quite straightforward.
Which one? Where's the what page?
Sorry, you just scrolled away from it. There are exercises in italic.
I see the exercise.
So the first exercise is quite like straightforward. I don't know if anyone wants to give the examples, like interesting examples from the top of the head. Go on, please.
Yeah, I guess you could imagine a self-driving kind of vehicle. And in there, the environment could just be represented by the camera input. The actions that can be possibly are accelerator, in the steering wheel, and the brake. And the reward function is obviously sticking to the road and not smashing into something and getting killed, I guess. And in that case, it is an MDP because the you don't need the full history of what's happened to the car. You only need to know the current state, what's currently visible on the cameras.
Well, yeah, but also you need to make it MDP. You need to include some extra information. I guess, for example, for a car, we probably want to like know its acceleration, and like so the state, probably the full state we need for solving the self-driving problem would include some extra variables together with the observed ones, right?
Yes, you would need to know what the current speed was, the current direction, and I guess some notion of where it's going. But the important thing is you don't need to know the full history. You just need what's happening right now, and that you should be able to use that to be able to plan where you're going.
Yeah, and a very simple one would be, say you're going to invest in the stock market, and you could make it as simple as possible and say, I'm going to pick one stock and I'm going to invest in that stock. And my action every day, I'm either going to invest in the stock or not invest in the stock, and then track the reward that comes from that. And the only thing you need to know is the current stock price. And it wouldn't be a very smart thing to do, but it's I think it's an example of a markup decision process.
Yeah, and again, you can extend your state to include like history up to like, I don't know, 100 steps, days, say, or a year back, and it still would be markup decision process, but you will have this extended state, and that's still a markup decision process.
Yeah, and the state could also include not only the price of that particular stock. Let's say you're investing in Apple stock or whatever. You're only going to invest in Apple stock, but you take into account the prices of all the other stocks on that day. You know, the state would include not only the price of Apple stock, but the price of all the stocks on the market that day. Or you could do it that way.
Yeah. I mean, in theory, the state can have some notion of what's happened in the past. It's got to encode it in the current time step.
Yeah,
you can't have like the full history available
right.
to it of what happened.
Right. It's a function of what happened in the past, but it has to be, like you said, it has to be encoded in the current state.
Yep. And what will be the parameter space with respect to the next state action, the rewards? How do you think we should define that with respect to the realistic distributions of the MDP or the transition state?
Do you mean for the stock buying example?
Yeah.
Well, the actions are you either buy or you either buy some, I guess it could be a real number of shares, or you buy, yeah, that's the only thing, is the number of shares that you buy is the action.
Yeah, I guess it's buy, sell, or hold is the action.
Then, yeah.
Yeah, holding is, oh, that's right, you can sell too, that's right. Yeah, holding is just buying zero. So,
yeah,
but yeah, buy or hold, buy or sell, yeah.
And the reward is the tricky one, because they've got an example later on where they're like, really the reward needs to be terminal, because you don't want to tell the algorithm what to do. You just want to reward it for doing the right thing eventually. So in some sense, it might be that, you might be a day trader, and you might be saying, well, I will definitely close out all my trades at the end of the day, and I just want to have a positive return. So yeah, the rewards are quite a tricky as to how you do them.
Yeah, but I guess as a first cut, you could just say the reward is the total value of my my Apple shares that that day. I mean, the difference between the, in other words, the gain, the net gain over that day's activity. You know, in other words, if I take a certain action if I buy 3.2 shares today, then what's my reward will be, I guess, the value of my portfolio tomorrow or something like that, or at the end of the day.
Yep.
Not the value, but the difference in value between yesterday's starting state and today's close.
And the discount factor can be modeled based on the time series predictions of the future states. In suppose next 2 to 3 days, what are the expectations of the stock market? That can be modeled. The whole return can be modeled based on the rewards in the future. That might be the case. Yeah.
But is it true then that you can't evaluate this strategy until you stop? I mean, because you don't know what's going to happen in the stock market tomorrow or today or the next day.
Yeah,
Yep.
although I think in these sorts of models, you kind of assume you have a set of options that could happen. I mean, obviously, this is one of these where the state space would be astronomical, but the idea would be, okay, let's say you have purchased something. Well, the next state is potentially could go up by 5 points, could go down by 5 points. A multitude of things could happen, and each one of those has a slightly different reward. And so the state space is enormous, and you probably wouldn't be able to kind of really compute it, but that's the way you would model it. It would be all the states that it could be in tomorrow, or at each time step that you're interested in. I mean, let's say you're doing it every 5 minutes, tracking the stock every 5 minutes or something like that. I thought that's the way you would think about it.
Yeah, so I guess to limit the state space, you could do something like, say, I only get to buy the stock at a certain time, like at 12 noon Eastern time, whatever. That's the time I buy, and I buy only either one share or no shares. That limits things, I guess.
Yep. This can be broken down into episodic task in which your share market is open from morning to the evening, and every day you accumulate a reward, and for a week you can have a return, and based on that you can accumulate that to give a hierarchical information about the expected total rewards or the total return in the future time steps or weeks or months with respect to a current. But that's how are we going to model that because of the unpredictability of the environment. It might be difficult, but yeah, I think so with respect to the environment dynamics that can be done. Cool. I think so. Let's move on to the next question. I think so. This covers exercise 3.1, 3.2, and the 3.32. Because exercise 3.3, we have considered the problem of driving.
Oh yeah, sorry, I hadn't seen that.
Yeah, but there is like extra question we did not touch yet in 3.3 regarding where you like place this like what you treat as your actions, and yeah, so that regarding the formulation of the task. So the author proposes multiple ways you can define the problem of driving. So let's go through the examples. You could define the actions in terms of the accelerator, steering wheel, and brake. That is where your body meets the machine. Or you could define them further out, say where the rubber meets the road, considering your actions to be tire torques. Or you could define them further in, say where your brain meets your body, the action being muscle twitches to control your limbs. Or you could go to a really high level and say that your actions are choices where to drive. What is the right level, the right place to draw the line between agent and environment? So what are your thoughts on this question?
Yeah, so I guess it depends on whether it's a robot that's driving it or a human. If it's a robot, then yeah, you would need to control actuators and all sorts of stuff. But if it's a human, then trying to model muscles and actions on those would be, from my perspective, that would be too difficult. And you probably just say it's a human that's actually capable of pressing an accelerator and pressing a brake. But yeah, interesting.
Yep, I think so. This can also be modeled as a continuous MDP problem, and with respect to a robot or a self-driving car, and at that point, if we fully consider an autonomous machine, then because in the real world, or how actually the self-driving example or any autonomous examples, how it actually does it, it depends upon the inference and the whole pipeline, and then the action that it selects. So I'm just trying to say we can take that approach too.
If, for example, if you had a drone delivery service, right? It's important that the actuators, the drone has to decide what speed it should go at and what direction it should go at, and how to avoid obstacles in the way, and where the destination is. So I think that what drives the whole thing is you've got to program it. You have a high level abstraction. You say, this is where I want you to deliver the package, and then things flow from there. So there has to be more than one level to look at. You have to say, first of all, this is your destination, and second of all, this is your payload, and then you have to have a process for getting there.
Mm-hmm.
And the process for getting there is where you talk about the interfaces between the drone and its sensors.
Mm-hmm. Yep, totally.
And actuators.
Yep, and then it refers to the planning problem with respect to the route that it should take from point A to point B, and it might depends upon the environment. Suppose if we take a drone, for example, then what's the airspace of the route that is free, as opposed to the crowded space, or what's the time it will take to reach from point A to point B.
Yeah, and since now at this point there are no quote unquote roads like we have highways, there are no defined roads, so it has to be done in real time. That is, the drone has to figure out if there's any other drones that are going to be crossing its path, and based on whatever sensors it has, whatever information gets passed to it, maybe it has its own sensors, and maybe it also has radio, some data is being beamed to it by radio that tells it the paths of other drones that it can't see yet.
Mm-hmm. Yep, true.
Okay, there is a question in the chat regarding exercise 3.2. So we should probably get back to it and consider examples. So what would be the examples when MDP is not a good framework to represent the learning task.
One would be if the states are time, if the environment is time dependent. I think.
So you think that if the environment changes with time, then it's not useful to formulate your learning task as MDP.
Or if your action had a delayed effect, that the environment changed in a way, you couldn't sort of say from this state in this action, I'm going to go to the next state. If that was, yeah, somewhere in that.
Interesting. So still we considered this non-stationary case in the previous chapter. We looked at the non-stationary case. So when the actual like reward distribution was drifting with time, and from that point of view, we still so that changes the best strategy we could take to solve the problem, but still we could kind of formulate it in a similar way, right?
Yep.
So we given the current state and our knowledge of expected rewards corresponding to some action, we still like even though if environment changes like smoothly, then it still would be best to act relying on what we know about the past rewards, right? And in this case, it basically this would allow us to formulate it as MDP. But if the environment like has discontinuities, the changes in environment are like discontinuous. Yeah, if you think of it like that, then probably yeah, there are some like problems when you formulate it as MDP, I guess. So.
And then also if the reward, if the reward given a current state and action wasn't deterministic, if there wasn't some determinism involved, then MDP probably wouldn't be the best way to formulate your actions, right? I mean, in other words, if you couldn't determine the next state based on your initial state, based on today's, based on your current state plus whatever action you take, if the next state was unpredictable, then maybe you couldn't do things. And I guess how you express that? Well, maybe if the distribution was flat for the next, if the probability of being in any of the, well, I guess if you have a current state and then you have a number of an integer number of states that you could go into from there, and the probabilities were all the same, then I guess you could do that as a Markov decision process. But what if the probabilities were just not uniform, but random in some way that you didn't know?
Yep, because it depends upon the Markov property, and that states that we have to know the previous set of states. And in poker, for example, there might be some more cases which totally is out of the distribution space of trying to predict the next state depending upon the so many how do I say it? So many actions or the states that it can take. So yeah.
Well, you need to know that transition matrix, and if you
Probability,
don't, and if that matrix isn't deterministic, then you don't have a hope of being able to track it as a Markov decision process.
But stochasticity can also work there. But I will have to take a look too. Let me.
I guess if you knew the probability distribution of what could happen next, but what if it wasn't known, or yeah, what if it wasn't known? What if it was just too random to be known?
It's talking about the goal-directed learning tasks. So,
I think examples will be evolutionary methods, isn't it? Because they basically ignore all the information from the states and the action statement.
Yeah.
I see. So yeah. So as long as there is a probability distribution out there to be found, then the evolutionary method could work. Let's see. So maybe we should try to make sense of some of these diagrams that we see all throughout the text. So starting in example 3.3. So the robot has a job of collecting empty soda cans. It has sensors that detect cans and an arm and gripper that picks them up and places them in a bin. But it can't run forever because it has a battery. And so it has to decide whether it's going to search for cans, or let's see, what does it have to do? Search for cans. Oh, it charging isn't one of the options. So it has to decide what to do based on its current charge level. Okay, so it can either search during a given period of time. It can wait for somebody to bring in a can, or it can go home to get recharged. Search, wait. Oh, so recharge is one of the options. Search, wait, and recharge are the three options. High and low are the two states of its battery charge. And then its next state is just described by how much is in the battery, either high or low again. So they've built a table of all the possible states and actions and next states, and it's 2, 4, 6, 8, 10. There are 10 entries in the table. Entries in the table.
Yep, the state action pairs. This is a tablet representation of the figure that we see on the right. There are two states. There are three actions. Basically, wait, search, and wait, and a probabilistic viewpoint based on the alpha and the beta variables. Here, alpha is, I think so, they have defined the energy level with a high probability, with a probability alpha, and the beta is the search when the energy level is low with the probability beta. So yep, these are the two variables that we take into account, and based on that, the next state that is conditioned on the state action pair is defined for each of the state action pairs.
Right, and since there are two states and 3 actions, I asked myself, why aren't there 2 times 3 times 2 results in the table? But then if you look at the last action is recharge, the third possible action is recharge, and you only take that action if you're in a low state. So that eliminates the other 2 states, high, you know, in other words, from a high state, you never go to a recharge state. Whereas from a high state, you can go to a search state or a wait state. From a low state, you can go to all 3 possible states. So that's why there are only 10 entries in the table. Alpha. So alpha is, I'm trying to figure out what is alpha and beta. What's the difference between alpha and beta? Alpha is.
So those are probabilities of going. So our next state is not deterministic in this case, but determined by some alpha and beta here. So those would be probabilities from state S doing action A. We go to state S prime with probability alpha, or another state S prime with probability 1 minus alpha, right? We have 2 states, 2 possible states, high and low. And with probability alpha, we go from state high doing search. With probability alpha, we go to state high. And with probability 1 minus alpha, we go to state low.
So alpha and beta are just the probabilities that result from taking various, taking a search action on any of the, from either a high state or a low state. It's the outcome of the search. So alpha and beta have to do with the outcome of the search, right? So if you're in a high state and you search, the probability that you'll still be in a high state is alpha. But if you're in a low state and you search, the probability that you'll still be in a low state is beta. And then the other 2 probabilities follow, the 1 minus alpha and 1 minus beta follow from those 2 given probabilities. So if you wait, you don't lose any battery charge. So the probability that if you're high and you wait, you'll still be high is 1. The probability from going from a high state to low state is 0 if you're waiting. So apparently waiting doesn't use any battery. If you're low, you can't ever get back to high by just waiting. And if you're low, there's only one possible result. If you wait, it's just you're going to be low again. Your next state is also going to be low. And then there's a reward. I guess there's a probability that you're going to get some cans if you wait. That's our wait, right? That's a expected number of cans you're going to get. Is that the correct way to interpret our wait?
There's a separate case too with respect to if the robot has to be rescued, it gets a reward of -3.
Ah, okay.
So that's what the third state action pair. The third column represents. So yeah, we have to take that into account too. And if no cans can be collected during a run of home for charging,
but how do you get, let's see, I don't understand this entry, the row that has the -3 at the end of it. Like you said, you start low, you start in a low state, you search, and you end up in a high state. How does that happen? How does that happen? How can you end up?
Because the action that you took was, it was search. So you were quite optimistic, but then suddenly you ran out of battery. So someone found you or found the robot and charged it. So the next time, the next state for the robot will be high, but it wasn't.
Oh, okay. That's a rescue. So
recharge.
that means in order to get from a low to a high state using search, that means somebody found you and recharged you. Is that it? Okay. But nobody will come looking for you if you're just waiting. I guess that's right, because there's no way to go from a low state to a high state through waiting. Right?
Right. Somehow.
It's just that if you're waiting, you have the possibility of getting rewards by someone
Yes.
handing you the can.
Yes.
Versus if you're in recharging, I think it says somewhere here that if you're recharging during the time, you have no possibility of collecting rewards.
Right. But if you're searching, if you're low and you're searching, you still have some probability of collecting rewards, but you also have some probability of running out of battery, I guess. That's that row that that has a -3 in the last column. You're low, but you decide to continue to search. And somehow you ended up in a high state. That must mean, as someone told us, I don't know your name, was that, let's see, who was the one that mentioned that? Try to remember, is it Garcia? Is that you?
Yeah, it's me, Garcia. Yes, sorry.
Yeah, what's your first name?
Miguel.
Miguel, yeah. Okay, so Miguel told us that the only way that happens is that if somebody rescued you, and then that's how come you ended up with the high charge, and then you get a negative reward, I guess. Even if you were, I guess, even if you had collected some cans during that search time, but then you ran out of battery, those cans don't count, I guess.
I think so, yeah.
Yeah.
They just get ignored.
Are they though? Because I guess in that case we would kind of break the learning process. So so those are rewards for state action next state triplets, and so it would be like a part of the as we will see later, it will be incorporated into the rewards of the previous decisions through discounting, but this -3 is the reward for this particular state action like outcome triplet.
Right, but if this outcome triplet, so if you start low and you're searching, and then somehow you had to be rescued, then you get -3 regardless of how many cans you collected while you were searching, I guess. So that's the point that I was thinking to make, is that even if you had collected some cans, they don't count against your reward. They don't count towards your reward if you had to be rescued.
Yeah, actually the way to think about it is there is low search low beta where you're going to get R search, right? So you're going to get that reward. If you're low, if you're searching and you still stay in low, you're going to get that R search.
Yeah, but let's see. But that's a different outcome than if you were low and you somehow had to be rescued. That's a different outcome, right?
Yeah, but I think the idea is you're in low, you're searching, and then you accumulate two cans, then you get that as reward, and then you continue searching, and then during that process you get depleted, and because you get depleted, you need to get rescued. After you get depleted, you can no longer collect any cans.
Okay, I get it. Yeah, that's a good point. Yeah, that makes sense.
Cool. So we should move on to the next section.
Sure, but let's look at this diagram just to make sure we understand it. So to see that it really represents the table. So if you're high, you can either wait and stay high. You can search and stay high. you can search and deplete your battery. If you're low, you can wait and still be low. I see. So what I think it was, what was it that just mentioned? Vishnu, is that the one that, were you the one that just mentioned that the way that as long as you're low and you're collecting cans, you do get those rewards, but then as soon as you, from the low state, you as soon as you have to be recharged, you don't get to collect any cans from that for that process.
Yeah, that's right.
Yeah. And yeah, so that makes sense, doesn't it? So, okay, let's move to the next. I'll get my arrow back. Well, I'll just. Okay. Did we want to move to exercise 3.4 or?
Yep.
So
Here in exercise 3.4, they say that instead of having 3 columns, probably, but for it should have columns state action S prime, that's the next state, and the reward. So and this has been reformulated from a 3 tuple to a 4 tuple case. And for it, I think it asks us to reformulate this table with these 4 tuple for which P next state reward conditioned on the state action is greater than 0.
okay, I have a
So-
stupid question, and that is why? I mean, why is this any different than just switching columns 4 and 5 in the table 3?
Yeah, that is, I think so. It's because of the next state reward. Here, we have to focus more on the reward part too. Because in the earlier example, we didn't, we focused on the action.
Yes. The only difference that I see is that it only wants rows for situations where the probability are greater than 0.
Mhm.
Oh, no, it's different because it's the probability is different, right? Because in the table 3, probability is the new state conditioned on the old state and the action. But in this table that they ask for now, the condition, it's the probability of the new state and the reward that you received from the old state, given the old state and the action. So I guess it is different.
Yep. In the last 3 lines, they have specified the environment dynamics with respect to the arrows that they have, the triplets of the box here on the page number 53. So let me try to here. They have defined it. The transitions. So the environment dynamics here, the transition graph, which respect to the state and the action nodes. You can this will require a bit of a pen and paper, so we can try this offline if everyone agrees.
So let's proceed to the next exercise.
.5.
Mhm.
Okay, so sorry, the equations in 3.1 are for the continuing case and need to be modified very slightly to apply to episodic tasks. Show that you know the modifications needed by giving the modified version of 3.3. So let's go back to 3.3. What is 3.3? 3.3. Okay, it's the sum of the conditional probabilities but marginalized over reward and action. So these sums, so he's talking about a continuous distributions, I guess. And so R and S, sorry, it's S prime. I was seeing it wrong. So it's marginalized over the outcomes, marginalized over S prime and R, where those are considered continuous.
Mm-hmm.
And now he says, what is it? How would you change that equation to if it were discrete? I guess that's what I interpret the question as. Is that what
Yep.
you, yeah?
Yep.
So first of all, why isn't he using integrals to cover the continuous case? I don't know.
It's not continuous and discrete, but continuing and episodic, which.
Okay, in time. Okay, so continuing in time and episodic in time. Okay.
Yes, I guess there's a state where you'll always stay in the same state, where if it's episodic, isn't it? Because they're modeling the terminal state of the episode as all the actions lead to the same state. So it's just, I mean, this will be that equation 3.3 will work all the way until the final state. And I guess that's the bit where you have to somehow slightly change it.
Oh, that makes sense.
So this is okay. Yep. So here
it will be from S to T, right?
So you'd have to put another summation over that where
I mean, the first summation will be starting from S till T, which will be the last state, or ST, better said.
Are you able to, yeah, you're able to jump in and annotate that the way you're suggesting, right? I think you're allowed to come in and annotate, I believe, because Mayank did that.
I don't know.
Let's see. I want, let's see. Oh, I thought somebody annotating the way they wanted to, or let me do it then, because so somebody suggested that we start with we're summing over time from t equals 1, where time corresponds to let's see, s prime s maybe sorry, let me try something. I'm not used to this system here. I want to, so the S is the states correspond to times, right?
No, so I think we're probably looking at something special about the terminal state. So if we choose S terminal or something like that, so if you condition it S terminal and any action, then it'll lead you to the same, would be with probability 1, and any other state, it'll be probability 0. I guess it would be something like that, won't it?
Not sure I get what you're saying.
So if we're at a terminal state, no matter what action we take, we'll stay in that state. We can't go to any other state. So the probability is 1 to stay in the same state, but probability 0 for any other state, I guess. It would be the sort of thing I'm thinking of.
Yeah, but I think there are no actions defined at the terminal state, right? So maybe we just like remove terminal state from the state space and this equation is done.
You still need something to lead you to the terminal state. But I think in the model they do have an action, but it's just always just goes back. It just keeps looping to the same thing, and you don't get any reward for that action. Basically, its reward is 0.
Yeah, we can go to the diagram in the book regarding that terminal state Arshad mentions. There is like an illustration. How do you relate this terminal state, like episodic, as to continuing using this terminal state?
Yep, I do.
Yeah, it's on page 57, the diagram for that one.
Let's see. I want to get rid of my pen here. Oh, I have to get rid of it through here. There. Okay, so now I should be able to get to page. What page did you say it was?
57.
57. Okay. Is this the right page? Or it's 57 in the, I think you mean 57 on the book, huh?
Yeah, 57 on the book. Sorry.
Okay, so yeah. I have to add 22 pages to that. So that's 79.
Yeah, it's there.
This
on
is the
left
one.
answer. Yeah.
Oh, okay. So reward. And then when you get to the terminal state, you always go back to it. Okay. So the difference then between episodic and continuing is that episodic implies a terminal state, and continuing implies that you can keep going forever. I'm not sure I'm understanding what that distinction is.
It needs to be discretized. For example, in the poll cart example, once that can be a totally continuous.
Yes.
If your pole does not falls over from one to the other side, whereas in an episodic case, there may be, I think so. We can also treat this as a continuous case because using kind of a discounting, but if it falls, then it will be an episodic task because it will learn based on the previous examples. So that will be the distinction between same problem that has been applied to both the cases. So the discretized as well as the which is the episodic task. If it falls, then we begin or restart based on that particular time interval. And if we have a kind of a discount factor that has been applied, then we can have the same poll example to be a continuous case. So in that, as they have alluded to in the example 3.4, if we give the return as minus gamma to the power k minus 1, where k is the number of time steps before failure. So that's how we can convert this to a continuous task. So
Well, so is that, let's go back to what that, because now I've lost sight of the question. The question was somehow asking how to convert between episodic.
continuous, yep, and episodic task. I think so.
Okay.
That was
Okay. So the cart is an example of a continuous. The cart poll example is an example of a continuous task, right? It never ends unless the poll falls. But you're suggesting that even if it ends, you can continue it from there, and based on what you've learned, and so in that way you can make it a continuous task that never ends.
Yep.
Is that what you're saying?
Yep.
Okay.
Successful will always be a positive reward, and it can continue to infinity. So that is by default episodic task, but we can convert it into a continuous case. And
but is this equation 3.3, is that for an episodic? I mean, is that already defined for a continuous task? And then they're asking how to modify it for an episodic task. Is that what the question is?
here it's being taken as is. I think so. Auto defined this here. This was by default they have taken it as continuous.
Okay.
No, I think so. It's a sequence of discrete time steps.
There's no
now I'm
mention of
confused.
time steps.
Yeah.
There's no mention of time steps here. So I think this could be taken as a continuous case. And then what someone was proposing is, I think it was Arshad, right? Arshad, you were saying that you can modify this by making it terminate. And then
Yes.
somebody was putting that in place somewhere. I forget where. You put it here, right? Or
yeah, I mean, I'm thinking that one way to do this would be to keep equation 3.3, but just to say that S is not the terminal state. So that's one case, and then have a separate version of it where S is the terminal state, and then the probability is 0 for all the other states. So yeah, so 3.3 doesn't work for the terminal state. So I would have just an extra condition saying that S is not equal to the terminal state.
Mm-hmm.
And then for the specific terminal state, I would have an extra equation like that, but where the probability is 0 now, because you can't go anywhere.
Okay, so you just add an extra case. So that equation is case where S is not the terminal, for all S in S minus terminal state or something like that, right? And then and then the next line would be probability is the probability of that expression for the probability is 0 if S is that terminal state.
So in my understanding, we add this terminal state as like a construct to reformulate episodic task as a continuing task. So that would unify both ways to think about it. If we add the terminal state to the episodic task, we would get a continuing formulation with an episodic, with an terminal state, which is kind of infinite, right? So yeah, that's probably the difference. You can easily reformulate an episodic case into continuing one by introducing this terminal state, which is like always cycling back to itself with no reward. And if you introduce this terminal state, then this equation would hold, because in case when the S here is a terminal state, and S prime will be always terminal state too, and the probability of getting from terminal state to terminal state would sum to 1 over all possible like states. It would be 0 for everything else and 1 for the terminal state, and that would make that equation holds. But if we don't introduce the terminal state, then we would like have to add this exception that when we would have this notion of final action, right, which stops which ends the episode.
Yeah,
I guess I don't. Yeah, I guess I don't understand the distinction, Arto, between what you just said and what Arshad said right before.
Yeah, my approach was a bit more convoluted, and his is actually much simpler. So he's saying, given that we have all these states in the episodic one, we just add one more, and the only probability for one is from that state to itself, and all the other states, the probability is 0. The p that we've got in that equation, because we define what that probability distribution is. So yeah, his is a simpler way of doing what I was trying to do. Yeah.
But it basically means kind of the same, right? If we don't have this notion of terminal state, then we got to specify this special case here for this equation. And if we introduce a terminal state, then the equation holds for all states, because for terminal state it holds also.
Yep. So there are to conclude. Then there will be 2 ways to do to solve this problem, and then which will be more optimal in the case of if we try to implement them with the memory, and because in the first case we will need to reformulate it and add a new state here, and in the second case we might need to have that time or that to insert a variable there to include condition or a threshold, which will result in a conditional statement. So what do you guys agree on, which will be the most optimal way to solve this?
So is this what Arto, is this what you're saying, that we just make this definition of this terminal state such that if, I'm sorry, my writing is not clear, but we have 2 cases, either S is the terminal state or it's not. And if S is the terminal state, that's this first line, then the probability of going to I guess I should say if S is the terminal state, then let's see, then the probability of going to another state S prime is 1 if the new state is still the terminal state, and is 0 if the new state is not the terminal, to go to any other state than the terminal state. So I guess if I write this, let's call ST the terminal state, then so then if ST is the terminal state, then the probability of going to another state S prime is 1 if that other state is ST, but is 0 if that other state isn't ST. Is that what you're trying to say?
And for terminal state, our action doesn't matter actually. So that would, it doesn't matter if we include it or not into the equation.
And then, okay, but just by adding the terminal state, then you make the whole thing terminate. Is that what you're saying? In other words, that's by introducing a terminal state with this property as one of the possible states, then that makes the thing terminate eventually.
By introducing the terminal state with this property, we will have I don't know. It would still be we will have sum over all states over all rewards of probability equal to 1 given terminal state, right? And action doesn't matter in this case, and the outcome will be always a terminal state. Yeah, but I'm not sure how do we put it, if it's even like what would be the like short, concise way to rewrite this equation for the.
Well, what you're saying is that the same equation applies in the new case as, in other words, after you introduce a terminal state, this same equation still applies, but the only difference is that there exists a state which has this property, that it ends everything.
Yeah, I guess the slightly confusing bit is that what our author was saying is that, we were written P of ST, comma, R, or, conditioned on STAT. We can't quite say that that's equal to 1 because that's across all actions. So the original equation is probably the right thing. What the probabilities we give the different actions on the terminal state, we don't really care. They just always add up to 1 because you're always going to stay in the same state. Yeah, so the only confusing bit is that we can't say that the probability that we've just written there is equal to 1 because if the sum over all A, then that is true, but not just on its own, the way we written it.
Oh, okay. I see. Yeah, that is a little confusing.
Yeah, I just want, we are probably running out of time, and I have just one question I wanted to ask quickly, and if someone can like clarify that for me, that would be nice. So let me name the page. Yeah, so it's page 60.
Okay. Which is 82.
Yeah, and probably we are skipping some part of. So here is an example of the grid world, and example for state value functions for equiprobable random policy, right? At the right. So and consider this action state A, denoted as A, and for this state, if any action leads to reward of +10 and leads to the state A prime, right? And here they like evaluated with a random policy. They evaluated the state value function for this grid world, and A has a value of 8.8, and I don't quite understand how could it be less than 10 if any action has a reward +10, and as we define the value here, so the value is reward plus discounted reward from the kind of. Oh, okay, all right. So yeah, I got the answer.
Oh, could you explain it to the rest of us, because I'm not quite understanding the problem.
No, but here is no confusion. Or actually, I just was confused because I didn't realize that here is the negative value for a prime, and it's like kind of subtracted here from R to get the value for A. So the value of A is 10 plus negative 1.3 multiplied by 0.9.
Yeah, I think the intuition there is once you're in A prime, you can always take an action to leave the grid. So I think that's why A prime, you have a negative value there. And then because there are chances of negative reward there.
Yeah. But I would guess this is kind of empiric, right? And it just kind of unlucky run probably or something.
Yeah, because it's you're taking a random policy, right? So the random policy can always take you off the grid.
Yeah, I get it, but I wonder if that's actually what are the values to which random policy would converge, or just a sample of like running a random policy and observing the reward.
Yeah, it does not sound like the policy ever starts using the value at all, right? It's always random. It's always going north, south, east, west, equi probably.
Yeah, but
Yeah, but this might need some sort of a model-based approach too. I mean, if we have a policy that for a discounted case in which we initialize the environment dynamics, then based on okay, so this can also be formulated as dynamic programming example too, but here we are collecting the transition rewards as well. I think the transition rewards are not known initially, right?
Can someone say what is in the table? What are those numbers in the table?
those are values of a state under random policy, with each action being equiprobable.
And the value is what? I mean, I don't understand the difference between value and reward. Is the value just the sum of all the rewards, or?
And the value is defined.
The weighted sum of all the rewards?
No.
Is defined at the left part of the screen, right? Here is v sub pi over of s is, and here is the definition of it. That's expectation given a policy of this g of t given s of t equals s. So for each state, we have an expectation of return, expected return, and the expected return is a reward for given like for the reward we receive for next for moving to a next state, and a discounted return for the next state. So here, if you look at it, the reward for any action, if you are in state A, it would be plus 10. And also we need to accommodate this the
0.9. So would it be then you have 4 possible actions. North gives you a reward of -1. East and west give you a reward of 0, and south gives you a reward of 10. And then, but all those rewards have to be
it is this special state A. Any action would reward you, will yield a reward of 10 plus 10.
I thought it says if you go north, wait a minute.
Doesn't matter where you go, you will still get 10.
Oh, I see.
10,
But I see.
and,
I didn't read that
to
carefully.
the A prime state.
Yeah. Okay. So where did we get the 8.8 then?
So 8.8 is 10 plus, you can look at the formula, so yes, 314, it would be 10 plus gamma, which 0.9 in this case, and multiplied by negative 1.3, which is the expected return for state A prime.
Okay, but what about the other transitions you could have made off grid? Shouldn't they have a negative reward that contributes to A as well? Oh, okay. This is just the reward from going A to A prime. Okay.
Yeah, and that's what I missed, is that the state A is special because all 4 actions give a reward of +10 and take you to A prime. But I guess it conflicts with the statement before that, though, because it says that all actions that cause the agent to move one cell actions that would take the agent off the grid leave its location unchanged, but also result in a reward of -1. So, yeah, I mean, if you start at A and try to go north, you get back to A and you get a reward of -1. So, wouldn't that be like
that's
infinite?
true for all states except A and B. So
Okay.
It doesn't apply to these 2 states. Here.
Okay. And is 1.3 just a give? Is minus 1.3 for state A prime? Is that just a given, or is there a way to calculate that too?
I think you can calculate using 3.14, right? So where you have a probability, like whatever 0.25 probability of leaving the grid, which is like -1, 0.2 probability of going up, going left, going right. So you just have to calculate all of these probabilities across.
Yep, I think so. It depends upon the figure 3.5. If you go to page number 65, here the actions are on all the
Oops,
4
I'm sorry.
directions.
Wrong way. 65, you said?
Yep. So I was pointing the differences between this problem on page number 60, the figure 3.2, and the page number 65. A similar kind of a problem with.
Wait, we're getting a little confused about the page numbers. So the book page 65 in the book is 85. Okay.
It's example
sorry,
3.8.
87. It's 87 in the book. Sorry. Yeah, there. Okay. There's 65.
Yeah. Here the actions have been defined with respect to the agent where it can visit in each of the cell states. In the above example, we had all the 4 left, right, up and down. Here only we have 1, 2, 3, or all the 4 transitions that a particular agent can visit. So depending upon that, we define our policy space with respect to the equation that the value iterations that we had, the Bellman's optimality equation that we saw. I think so. Yep. So that's the value. How do I say it? The value, the V star here, and so similarly. This is the optimal solution here, which we see on page number 3.a, which they have solved it. And
what do the arrows mean then? I mean, because how do you represent the case from starting from A getting to A prime? I mean, it just has 4 arrows there.
yep, from A to A prime, then we have to go like this. We will have to find an optimal path from going
Yeah,
from
A
A
to A.
to A.
Yeah, I think A to A prime is because of that special state, right? Because it doesn't matter what you do, you're always going to go to A prime.
Okay. But the arrows themselves, does that just represent the possible moves that you have when you're in that state?
No, it's
Optimal.
optimal move.
Optimal move. Okay.
And that's denoted by star. That's an optimal policy, and this is like depiction of the optimal policy.
Okay, got it.
Yeah, I think it's really good to see example 3.5 and 3.8 together. In one, you see the random policy. In the second, you see an optimal policy.
Ah, okay. Oh, okay. Okay, so the other one, 3.3 was, or this was the random policy, right? 3.5. Yeah.
I think so. We will discuss on this the next time too. Because
Yeah, let's end here. Yeah, because
yeah.
we don't want to go over so far.
Mhm.
Yeah, thanks for coming. And I guess I don't know if we should move on. I think we should stay in. I think it wouldn't be a
Yeah.
good thing to move on to chapter 4. We should just stay in chapter 3 and try to get through it.
Because this
Okay.
is the fundamentals, and if we do not clear every aspect of it, then we might have issues in the future with respect to the rest of the book.
Yeah, at least to get a basic understanding of chapter 3.
Yep.
Okay, everyone, thanks. I'm sorry that I didn't watch the time, and next time I'll try to keep it to 2 hours. Okay. See you next week. Bye.
Thank you.
Thank you, guys. Take care.
Thanks, everyone.